Hello, everyone, and welcome to this explainer. Listen to me very carefully today because we are going to dive into one of the most fascinating, mind-bending two-way streets in all of physics. Today, we are completely mastering a crucial study map based on the Selena textbook chapter on electromagnetism and induction. Now, I want to start with a hook. Have you ever just stopped and wondered how the silent, invisible electricity in your wall socket magically transforms into the loud, physical, spinning motion of your washing machine or a giant factory motor? If you have, you are in exactly the right place. We are going to visualize exactly how these two fundamental forces of nature, electricity and magnetism, are actually perfect mirrors of each other. By the end of this session, this entire concept will be crystal clear. Let's get started.
Here is our roadmap for today's session. First, we'll see how electricity creates magnetic fields, and then how we can control them. Third, we'll harness the motor effect. Then we hit the great reversal, induction, followed by powering the generator effect, and we will wrap it all up with an epic showdown between AC and DC power. Section 1. Electricity creates magnetic fields. This is where the spark of our journey really begins. Our story begins way back with Hans Christian Ørsted and his famous experiment. Picture this. He's doing a lecture. His setup is incredibly simple, and he discovers this almost completely by accident. He finds that simply running an electrical current through a straight, ordinary wire caused a nearby magnetic compass needle to suddenly deflect. Now, you might be thinking, okay, so what? Well, imagine a student asking, but why did the compass move if there was no magnet nearby? And the answer is the absolute light bulb moment from modern physics. The compass moved because the electricity itself created a magnetic field. It proved that an electrical current isn't just energy moving invisibly through a wire. It is actively generating an invisible physical magnetic field all around it in the space outside the wire. Mind-blowing, right? So electricity creates a magnetic field. But how do we know exactly where that invisible field is pointing? What's its direction? To figure this out, we use a brilliant little trick called the right-hand thumb rule. I want you to literally do this with me right now. Hold up your right hand, imagine you are grabbing that straight wire, and point your thumb in the exact direction the electrical current is flowing. Now look at your fingers. The way your fingers naturally curl around that imaginary wire shows you the exact circular direction of the magnetic field wrapping around it. Simple, right? And this exact same rule dictates the distinct, highly concentrated magnetic field pattern you get when you take that straight wire and bend it into a circular coil. Section 2. Controlling the magnetic field. Now that we've created it, how do we tame it?
Okay, so we have a basic magnetic field, but a weak, tiny field around a single wire isn't going to lift heavy machinery. How do we make it truly useful? Enter the solenoid. A solenoid is what happens when you take that wire and tightly wrap it into a long coil, almost like a spring. When you run current through it, all those tiny individual magnetic fields combine to create a beautiful, strong, uniform magnetic field running straight through its center. And here is the best part. We have total control over it. If a student asks, how do we make it even stronger? The answer is simple. We can increase the strength of this field by doing just two things. We can either increase the number of turns, meaning we wrap the wire coil tighter and more times, or we can simply pump up the magnitude of the electrical current flowing through it. More current or more turns equals a stronger magnet. This brings us to a classic exam question, so pay close attention. How does our solenoid compare to a traditional bar magnet? Well, both of them have a distinct north and a south pole, and if you map out their magnetic field lines, they look almost identical. But there is a massive, game-changing difference. The key word here is control. A typical bar magnet is permanent. Its strength is fixed, and it is stubbornly going to stay a magnet no matter what you do. But our solenoid, its magnetism is temporary. It is entirely adjustable based on the current we feed it, and we can shut it down instantly. And we can take that solenoid one step further. By taking a piece of soft iron, specifically a soft iron core, and placing it directly inside that hollow solenoid coil, we construct what is known as an electromagnet. That iron core massively amplifies the existing magnetic field. This gives us a wildly powerful, completely controllable magnet that we can turn on and off with the literal flick of a switch. This is the exact technology you see in those massive junkyard cranes lifting entire cars, all the way down to the tiny vibrating speakers inside your headphones. Okay, quick revision time. Chapter 1 and 2. Electricity flowing through a wire creates a magnetic field. We find its direction using the right-hand thumb rule. If we coil that wire into a solenoid and add an iron core, we get a super strong controllable electromagnet. Concept clear? Let's move on. Section 3. Harnessing the motor effect. Let's convert that invisible electricity into real physical motion.
We have established beyond a doubt that a wire carrying a current creates its very own magnetic field. So imagine this. What happens when we place that current-carrying wire directly inside another, completely external magnetic field, like, say, wedged between two large permanent magnets? Well, the two magnetic fields are going to clash. They interact, and because of this clash, the wire experiences a literal physical push, a true mechanical force. We call this the motor effect. This is the magic moment where pure electrical energy is converted directly into mechanical kinetic energy. And this is the fundamental principle behind the direct current, or DC motor, which uses this effect to do hard work for us. In a DC motor, current flows into a coil, the magnetic fields interact, and a force pushes the coil, making it turn. But wait, a very smart student might ask here, if it turns halfway, won't the wires get tangled, or won't the force just push it backward and get stuck? That is a brilliant question, and the answer is our secret weapon, the commutator. The commutator is a clever split-ring device that plays the absolutely central role of reversing the direction of the electrical current every single half turn. Because it constantly flips the current, it ensures that the physical force keeps pushing in the exact same rotational direction. This means our coil doesn't get stuck, it rotates continuously, giving us a working motor. Quick revision of Section 3. Current plus an external magnetic field equals physical force. The commutator keeps the DC motor spinning in one direction. Got it? Let's keep going.
So the absolutely crucial point we've learned so far is that electricity creates magnetism, and through their physical interaction, we get motion. Electricity creates motion. But that leads us to our big, dramatic pivot question for this explainer. Think about this carefully. Can we drive the street in reverse? If electricity can create motion, can physical motion create electricity?
Section 4, the Great Reversal, Induction. Welcome to the perfectly mirrored opposite side of physics. Thanks to Faraday's law, we know that the reversal is absolutely 100% possible. We call this phenomenon electromagnetic induction. Faraday's law states that simply changing the magnetic flux around a coil of wire will literally induce an electrical current within that coil. Now, what is magnetic flux? Just think of it as the amount of invisible magnetic field lines passing through a specific area. If you change that amount by moving a magnet closer to or further away from a wire, you force electrons in that wire to move. No batteries are required for this. Just take a physical magnet, move it near a coil of wire, and boom. The physical motion of changing that magnetic environment creates electricity. Motion creates electricity. It's beautiful. But, of course, nature doesn't just give us free energy without a little bit of a fight. There is a catch, and it's beautifully summarized by Lenz's law. Lenz's law states that the induced current will flow in a specific direction that creates an opposition to the change that produced it. Let me translate that into plain English. Nature is stubborn and always resists change. If you take a north magnetic pole and push it forcefully into a coil of wire, the coil doesn't just sit there. It will induce a current that specifically generates its very own north pole right at the entrance to repel your magnet. It will actively, physically fight the motion that created it. You have to do actual mechanical work to overcome that repulsion, and that mechanical work is what gets converted into electrical energy. Quick revision of Section 4. Moving a magnet near a wire induces electricity. That's Faraday's law. But the induced current will fight the motion. That's Lenz's law. Section 5. Powering the generator effect. Now let's see how we harness this great reversal to power our modern world. Before we can build a working generator, we need to know exactly which way our newly induced current is going to flow. Hold up your hands again for me. Earlier, we talked about Fleming's left-hand rule, which we use to find the direction of physical force in motors. But remember, generators are the exact perfectly mirrored opposite of motors. So, logically, you must use Fleming's right-hand rule to find the direction of the induced current in generators. Left hand is for finding the motion in motors. Right hand is for finding the electricity in generators. Never mix them up on an exam. So, putting all of this theory into practice, we build the AC generator. Here is how it works. We do the mechanical, rotating ourselves. We might use a massive steam turbine in a power plant or water flowing over a dam to physically spin a coil of wire inside a giant magnetic field. Because the coil is spinning, the magnetic flux passing through it is constantly changing. And as we know from Faraday, changing flux induces a current. Now, remember the commutator from our DC motor? Generators don't use those. Instead, they use something called slip rings. Slip rings maintain a smooth, constant connection to the spinning coil, drawing out the raw, naturally reversing induced electricity exactly as it's generated, without flipping it artificially.
Because our coil in the generator is spinning in a continuous circle, the magnetic flux is constantly increasing, peaking, decreasing, and then completely reversing direction. When we map the output of this electricity, it creates a wave. This is what we call alternating current, or AC. It's a waveform that is constantly reversing direction, going positive, then negative, directly and perfectly matching the mechanical, circular rotation of the generator itself. Quick revision time. Section 5. We spin a coil and a magnet to make AC electricity. We use the right-hand rule to find the current direction, and we use slip rings to draw out that wave-like alternating current. Section 6. AC versus DC power. We have our DC motor and our AC generator. But the ultimate question is, which type of power is actually better? Well, it depends on what you want to do. Direct current, or DC power, flows continuously in one flat direction. It is absolutely great for batteries, laptops, and small electronics. But historically, it was terrible for traveling long distances. Alternating current, on the other hand, has massive, undeniable transmission advantages over DC. AC power can be sent across hundreds and hundreds of miles of thick power lines with very little electrical energy lost as waste heat. Because of this incredible efficiency over long distances, AC became the undisputed champion for building our national power grids.
But a curious student should ask, why exactly is AC so good at long-distance transmission? The secret lies in a brilliant device called a transformer. This is the ultimate superpower of AC. Because alternating current is constantly changing direction and constantly changing its magnetic flux, it naturally, perfectly works with electromagnetic induction. This allows transformers to easily step up the voltage to incredibly high levels. High voltage pushes the power across vast, long-distance highway lines incredibly efficiently. Then, once it reaches your neighborhood, another transformer steps down the voltage so it is safe enough to enter your home. DC power flows constantly, so it has no changing flux, which means it simply cannot use transformers this way.
Understanding exactly how that transformer-stepped AC power safely travels from the pole outside, gets into your wall sockets, navigates your household fuse box, and safely powers your appliances is a whole other fascinating story. We are going to explore exactly how all of that works in our very next explainer on household electricity and domestic circuits. Consider that your homework. Go look at your home's breaker box and wonder how the AC gets properly distributed.
We have covered a lot today. It's time for our final summary. We've seen electricity create magnetism to give us motors, and we've seen magnetism create electricity to give us generators. As we completely wrap up this syllabus map on electromagnetism and induction, I want to leave you with a final provocative thought. We have just proven that electricity and magnetism are not actually two separate things. They are perfectly mirrored reflections of one another, unified into a single, beautiful force called electromagnetism. If that's the case, what other fundamental forces in our universe are secretly the exact same thing, just waiting for us to discover the connection? Keep questioning the invisible forces around you, review your notes, and I will see you in the next explainer.